Hello, and happy to teach you another physics lesson. Today we'll talk about the Doppler effect. Uh, this is chapter 9, section 5. Okay, and as you can see, there's a Doppler effect for sound waves and for light waves. Okay, so we have the acoustic Doppler effect. Okay, sound waves. And we have the relativistic Doppler effect. Okay, which works for light waves or electromagnetic waves in general. And this is related to Albert Einstein's theory of special relativity. Okay, and there are some formulas that describe the Doppler effect for a moving source, for a moving observer. Okay, these formulas apply to the acoustic Doppler effect, so sound waves. And there's a third formula for electromagnetic radiation. You see it here. Delta F, change in frequency, delta lambda, change in wavelength. About V over C, C is the speed of light. So this tells you that you deal with light, with the relativistic Doppler effect. In the booklet, you have these three formulas. They don't tell you which ones are for the sound waves, which one is for the light waves, but you have to remember that. Okay, so first of all, what is the Doppler effect? The Doppler effect is an apparent change in frequency due to the motion of the source of waves or the motion of the detector or both. Okay, so the acoustic Doppler effect is an apparent change in frequency, change in the frequency of sound this is also called the pitch. High frequency is high pitch, low frequency is low pitch. So the acoustic Doppler effect is an apparent change in the frequency of sound due to the motion of the source or of the detector okay, what is the source of sound? Well, it could be, for example, a loudspeaker. What is the detector of sound? Example given, well, could be a microphone or your ear, yeah? Okay. Due to the motion of the source or of the detector or of both the source of sound and the detector could be moving, okay? Could be moving relative to still air. Okay. What's the meaning of still air? That means at rest. Okay. Stay still. Stay still means stay at rest. Don't move. Yeah. Okay. Now, of course, we could also look at a situation in which the air is moving, like during a storm or a tornado or who knows what, the wind is blowing. We don't look at that. That's too complicated. And we don't need to go into that much detail. Okay, now sound waves propagate through air. Sound waves are changes in air pressure, right? And you need the air molecules to have a pressure. And this is why we need to distinguish between the acoustic Doppler effect and the relativistic Doppler effect. The relativistic Doppler effect does not need a medium at rest because light waves, electromagnetic waves don't need a medium to propagate. Okay, so electromagnetic waves don't need a medium to propagate. Okay, so that's a big difference between the acoustic Doppler effect and the relativistic Doppler effect. And also, due to the theory of special relativity, okay, we know that the only thing that matters is the relative velocity, yeah? So there is no stationary ether. This is what Einstein proved, because before him, people believed that light propagates through a medium just like sound, and they assumed that this medium, the ether, fills all the space, but now we know it doesn't exist. Okay, and because of this, you cannot talk about the speed of the source relative to the medium, or the speed of the detector relative to the medium. You can only talk about the relative speed. Okay, and because of this, the definition of the relativistic Doppler effect is slightly different and looks like this. Okay, so the theory of special relativity. Tells us that there is no medium, no stationary, no special medium. Okay, ether. That was the name of the hypothetical medium needed for the propagation of light. Okay, no medium. And as a result, only the relative, only the velocity of the source relative to the detector matters. Only the velocity of the source relative to the detector matters. And we'll see this in more detail when we'll analyze the relativistic Doppler effect. For now, we start with the simpler situation of the acoustic Doppler effect. The acoustic Doppler effect. Okay. The first case one. Okay. The wave source is at rest. And the detector is at rest. Okay. So we have a source here. We have a source here producing sound waves. And let's say that at this moment, T1, I have a wave front produced. Okay, what is the wave front? The wavefront is the geometric place of all the points with the same phase. So, for example, maximum, maximum pressure. Same phase. For example, maximum pressure, air pressure. Maximum air pressure at this wavefront. And the wavefront propagates, moves with speed v. Okay, v is about 343 meters per second, speed of sound in air. This changes a little bit with temperature, but we ignore that. Okay. And after a period, at time t2, the source will produce another wavefront of maximum air pressure. By this time, the first wavefront is here. It has traveled a distance, okay, which is what we call the wavelength. Symbol lambda, the wavelength. It is the distance traveled by the wave in one period. Okay, so from here to here, this is the wavelength. And I can write, of course, what can I write? The period is t2 minus t1. Okay, the period of this wave. And the wavelength is the speed of sound times the period, yeah? Distance is speed times time. Okay. And later, this front reaches the detector. Here I have a detector at time t3. Okay, the first front. The second front is here in the back at the same distance, lambda. Okay. And even later, this front also reaches the detector at time t4. Okay, and the difference between these times, that's the period of the sound wave measured by the detector. Okay, t prime, I will call it t prime is T4 minus T3, the difference in times, yeah? And of course, this wavefront travels with the speed of sound v. So this wavelength, this distance, will be the speed times the time, yeah, v times t prime. And from these two equations, what conclusion do we draw? We draw the conclusion that t prime is equal to t. When the source is at rest and the detector is at rest, okay, the frequency heard by the detector is the same as the frequency produced by the wave source. Okay, this relationship is about the periods, but of course, the period and the frequency are related. Yeah, we know that frequency times period is 1. And that means that the frequency heard by the stationary observer is equal to the frequency produced by the stationary source. Okay, easy. So far, no surprises. Now, what happens if the source moves towards the detector? Okay, this will be case 2. Source moves toward the detector. Detector is at rest. Okay. Well, again, we have to draw the 4 important moments. So at T1, the source produces this wavefront, which propagates with speed v, 343 meters per second. And at time T2, another wavefront is produced, but this time it is not produced at the same position because the source is moving with speed vs. towards the detector. I assume that the detector is somewhere on the right. Okay, and by this time, the first wavefront has traveled also a distance. We find it here. Okay. And here in this diagram, we have three distances to worry about. This distance from here to here, okay? This distance from here to here, and this distance from here to here. Okay. What is this distance from here to here? It's the distance traveled by the source of waves. Okay, so first of all, the period is T2 minus T1. This is the same equation, yeah? The time between the emission of two wavefronts. So this distance is the speed of the source times the period. This distance here is the distance between two wavefronts. It is a new wavelength. It is the, okay, so this distance lambda prime plus lambda prime, okay? And this is equal to what? From here to here, what do I have from here to here? It's the wavelength when the source was at rest. Which was the speed of sound times the period. Okay. So because the source is moving, the distance between two wavefronts is no longer what it was. It is smaller. And when the wavelength decreases, the frequency increases. Okay. What's the equation that connects frequency and wavelength? The wavelength is the speed times the period. The period is 1 over the frequency. That means the wavelength is the speed over the frequency. That means the wavelength times the frequency is equal to the speed, which is constant, 343 meters per second, constant, yeah, which means that if the wavelength decreases, that means the frequency must increase to give you the same product. Okay. Okay. And then at the moment T4, this wavefront reaches the detector. This wavefront is still behind at a distance lambda prime. Okay, and even later, this wavefront also reaches the detector at a time T4. Are you kidding me? This is T3 here. Okay, and the period detected is T prime is T4 minus T3, just like before. Okay, but this time the new wavelength lambda prime is V times T prime. Okay. So now we'll have a different relationship between T and T prime. To help you with deriving this relationship, I will extract lambda prime from this equation. Yeah, lambda prime is equal to V minus Vs times T. Yeah, I move this to the other side. And then from this equation and this equation, what do I get? T prime is equal to T times V minus Vs over V. And in terms of frequencies, right? Frequency is 1 over period, so I just flip both sides. 1 over T prime is equal to 1 over T times V over V minus Vs. Okay, which gives me the formula. The new frequency is the frequency when both the observer and the source are at rest, times V over V minus Vs. Which is one of the formulas in the booklet. Okay, right here, moving source, f prime equals f times v over v minus, and they call the speed of the source us, I called it vs, same thing. Okay. Now what happens when the source moves away from the detector? Let's see, case 3. source moves away from the detector and the detector is at rest. Okay, so now at time t1, the source produces a wavefront. The wavefront moves to the right with the speed v. The detector is somewhere on the right, but the source moves to the left away from the detector with the speed vs. Okay. And later on, after a period, yeah, t is t2 minus t1, later on, the source produces another wavefront okay? But the first wavefront has traveled the distance. Now again, what are the distances that matter here? From here to here, this is Vs times t, the speed of the source times the period. From here to here, this is the wavelength when the source is at rest. And from here to here, this is the distance between two successive wavefronts. This is the wavelength, the new wavelength that we have. And the equation changes to lambda prime is equal to Vst plus Vt. Okay, which means lambda prime is V plus Vs times T. What's the difference from the previous case? This minus sign has turned into a plus sign. Okay, and then later on at the time t3, the first pulse, the first wavefront reaches the detector. The other one is behind at a distance lambda prime. And even later, at a time t4, this second wavefront reaches the detector, and the measured period t prime is t4 minus t3. Okay. the wavelength, the distance between wavefronts, is the speed of sound times the measured period, just like before. Nothing changes on this side of the detector because the detector is at rest in both case 2 and case 3. And again, putting together these two equations, we draw the conclusion that T prime is T times V plus Vs over V. We flip both sides. 1 over T prime is equal to 1 over T times V over V plus Vs, which means that the new frequency is the frequency when both the source and the detector are at rest times V over V plus Vs. Okay, you have to remember what is V in this formula. V is 343 meters per second, and Vs is the speed of the source. Moving away. Okay. In this formula, V is 343 meters per second, and Vs is the speed of source moving closer. Okay. Here I divide V by something smaller than V, yeah? Which means this fraction is less than 1. When I, excuse me, not the fraction, the denominator is less than 1. I divide by something less than 1, the result is bigger. Yeah, so in this case, the frequency is bigger. F prime is bigger than F. Here, the frequency is smaller because I divide by something bigger than 1. Okay, and this is something you should remember because this helps us memorizing the signs in the formulas. Okay. If the source and the detector are getting closer, the parent frequency, the heard frequency, the detected frequency gets higher. So we are in this situation. F prime is F times V over V minus Vs, which is F times 1 over, I divide by V up and down, 1 minus Vs over V, yeah? And this number here is less than 1. So I divide by a number less than 1, which means f prime is greater than f. The frequency gets higher. If the source and the detector are getting farther apart, the detected frequency gets lower. Okay, so in this case, the detected frequency, it's the frequency when the source and the detector are at rest, times V over V plus Vs, which is F times 1 over 1 plus Vs over V. I divide by a number that is greater than 1, which means f prime is less than f. Okay, and these two statements will be true also in all the other cases, and they will help us decide which signs, plus or minus, to use in the formulas. Okay. Case 4, source at rest. Source at rest. Okay. Detector moving closer. Okay. So at time t1, the source produces a wavefront which moves with speed v. At time t2, another wavefront is produced. By this time, the first wavefront has moved over a distance lambda. Yeah? T is t2 minus t1, the period, and lambda is speed of sound times period. Okay, just like in the case of the source at rest and the detector at rest. Now, what happens on the detector side? Well, at time t3, this wavefront reaches the detector. The other wavefront is behind, okay, at a distance lambda. This wavefront is moving with a speed v, 343 meters per second. But the detector is also moving towards the source with a speed v o. O for observer. Okay, detector observer. That's the notation in the IB booklet. So we just keep it. And later on, at time t4, the second wavefront meets the detector. Okay, and there are three distances we need to talk about. Okay, the distance traveled. Okay, first of all, this is the new period measured by the detector. T prime is T4 minus T3. Okay, we have this distance here. This is the distance traveled by the wave. This is V times T prime. We have this distance, the distance traveled by the detector. This is the speed of the observer times T prime. And we have this distance, which maybe you remember, it's the wavelength lambda. So now I can write V times T prime plus V observer times T prime is equal to lambda. Okay, so V plus V observer times T prime is equal to lambda. And now from these two equations, I derive the relationship between T prime and T. Yeah, so this is equal to this, which means T prime is equal to T times V over V plus V observer. I flip both sides of the equation. 1 over T prime is equal to 1 over T times V plus V observer over V, which means that the new frequency is the frequency when both the source and the detector are at rest times V plus VO over V. Okay. Okay, you have to remember that in this equation, V is 343 meters per second, plus or minus. This can change if the temperature changes, or maybe the gas can change. Instead of sound waves in air, maybe we have sound waves in, I don't know, helium, or maybe water waves on a lake. Who knows that? So this may change, but it's constant for a given situation. And VO is the speed of observer okay, moving closer. Okay. So far, so good. This is one of the formulas in the booklet. Let's look again at the booklet. We have it right here. Moving observer, okay, with the plus sign when the observer is getting closer. Okay. Now, what happens when the detector is moving away from the source? Case 5. The source is at rest, and the detector is moving away from the source. Again, at time t1, the source produces a wavefront that moves with speed v. At time t2, the source at the same position produces a second wavefront. The distance between the two wavefronts is lambda. T is t2 minus t1. Lambda is vt, the speed times the period. And then at a later time t3, this wavefront reaches the detector. The other wavefront is behind at a distance lambda. Okay, this wavefront moves with a speed v towards the detector, but the detector moves with a speed vo away from the source. And at a later time, t4, this wavefront also reaches the detector, but by this time, the detector has moved a little. It's here, okay? And the time between this wavefront reaching the detector and this wavefront reaching the detector, this is the new period, the measured period, T4 minus T3. Okay. And again, we have three distances to worry about. Okay. This distance, which is V times T prime, the speed, yeah, times the time, V times T prime. This distance here, the distance traveled by the detector in this time, it's VO times T prime. And this distance here, okay, which, as you remember, was the wavelength at the source. So now I can write lambda plus VOT prime is equal to VT prime, which means lambda is equal to V minus VO inside parentheses T prime. Yeah, I move this to the other side and I factor T prime is a common factor. Okay, now comparing this equation with this equation, I get the relationship between T and T prime. What do I get? T prime will be what? T times V over V minus V0. I flip both sides of the equation. 1 over T prime is equal to 1 over T V minus V0 over V, which means F prime is equal to F times V min minus V0 over V. Pretty much like in the previous case, yeah, but the plus sign now has turned into a minus sign. Okay, so V is equal to 343 meters per second. And VO here is speed of observer moving away. Okay. And again, we do the same analysis. If the source and the detector are getting closer, the detected frequency gets higher. Okay, because in this situation, the formula that applies is F prime is equal to F times V plus V0 over V, which is F times 1 plus V0 over V. So I multiply by a number that is greater than 1, and as a result, F prime is greater than F. On the other hand, if the source and the detector are getting farther apart, the detected frequency gets lower. Okay. In this situation, the formula we use is F prime is equal to F times V minus V0 over V, which is F times 1 minus V0 over V. I multiply by a number that is less than 1. And as a result, F prime is less than F. And That's what you have to memorize. If the source and the detector are getting closer, the detected frequency gets higher. If the source and the detector are getting farther apart, the detected frequency gets lower, because only in this way you will be able to pick the correct sign, plus or minus in the formulas given in the booklet. Now, we'll look at the next case, case 6, where both the source and the detector are moving. And just to keep a long story short, I'm gonna look at only one of the 4 possibilities. So source is moving towards the detector, and detector is moving towards the source. Okay. So at time t1, the source produces a wavefront which travels with a speed v. At time t2, the source produces another wavefront okay, which travels with the speed v. The period is t2 minus t1, and there are 3 distances we have to worry about. Okay, the source is also moving with the speed vs. Okay, there are 3 distances we have to worry about. From here to here, this is the speed of the source times the period. From here to here, the distance between the 2 wave fronts, okay, lambda prime, and from here to here, the wavelength when the source is at rest. Okay. So just like in case 2, we can write Vs times t plus lambda prime is equal to Vt, which means lambda prime is equal to V minus Vs times t. Okay, now let's see what happens at the detector. So at time t3, this wavefront reaches the detector. And the other wavefront is behind at a distance lambda prime. Okay. The detector is also moving towards the source with a speed VO. And this wavefront is moving towards the detector with a speed V. And at a later time, T4, the detector will meet the second pulse here. Okay. And again, there are three distances we need to look at. Okay. The period measured by the moving detector is T prime, which is T4 minus T3, yeah? And this distance traveled by the wave in the time T prime is V times T prime. Just like in case 4. In this distance, the distance traveled by the detector is V observer times T prime. Okay. And from here to here, that is lambda prime. Okay, so now we can write V times T prime plus V observer times T prime is equal to lambda prime. Okay, so V plus V observer T prime is equal to lambda prime. And again, we put together the two equations. Lambda prime is equal to this, lambda prime is equal to this is equal to this. So I have a relationship between T and T prime. What relationship do I get between T and T prime? T prime is equal to T V minus Vs over V plus V observer. I flip both sides. 1 over T is equal to 1 over T prime is equal to 1 over T V plus VO over V minus Vs, which means F prime is equal to F times V plus VO over V minus Vs. Okay, in this expression, V is 343 meters per second, for example. VO, speed of observer, moving closer, Vs speed of source moving closer. Okay, and as you may notice, it's like multiplying one fraction with the other. Yeah, the v's cancel, and what's left is v plus u0 over v minus us. Okay. So in general, okay, in general, the detected frequency will be the frequency when both the source and the detector are at rest, V plus or minus V observer over V plus or minus V source, okay? Which I may also very conveniently write F times 1 plus or minus V over V over 1 plus or minus Vs over V. Okay, and all I have to remember is how to pick the signs correctly based on the rule, yeah? So when do I pick the plus sign here? Well, this plus will make the frequency bigger. That means the source and the observer are getting closer, yeah? That means observer is moving towards the source. When do I pick the minus sign? Well, the minus sign will make the frequency smaller. That means the two are moving away from each other. That means the observer is moving away from the source. Okay. When do I pick the plus sign here? Well, this plus sign will make the frequency less than what it used to be. Okay, that means the two, the source and the detector, are moving away from each other. Okay, so the source is moving away. Source is moving away from the detector, the observer. And when do I select a minus sign in this formula? Well, this minus sign will have the effect that f prime will be greater than f, which means that we are getting closer to each other. Okay, so that means that the source is moving closer towards the observer. Okay, so that's how we select the correct plus or minus signs in the formulas. And you have to remember that the general formula is the product of the two formulas given in the booklet. Okay, f prime is f times yeah v over v plus or minus vs times v plus or minus vo over v. Yeah, so these two are given in the booklet. Multiply them together, and this v will cancel, and you end up with a more general formula. And I have derived only the case when the two get closer to each other. But of course, the same procedure applies to all the other situations. When the source gets closer, the detector moves farther away, or uh, same procedure. The sign here may change to a plus or minus. The sign here may change to a plus or minus, and that's how we get the four possibilities. Okay. The Doppler effect has very important applications. Okay. The Doppler effect has very important applications, which you have here in the booklet. Okay, the Doppler effect can be used to measure the speed of a moving object. Okay, you can measure the rate of blood flow, the speed at which the blood cells are moving, or you can measure the speed, okay, at which the clouds are moving, or you can measure the speed at which the cars are moving. Okay. Measure the speed of blood cells. Okay, and that's how you get the heart rate. Okay, the so-called Doppler sensor. A pregnant woman can hear the heartbeat of the baby in this way. Okay, speed of clouds. Okay, and that's good for weather forecast. okay? Or the speed of cars, okay? The so-called radar. This is done with the electromagnetic waves, but it's still a Doppler effect. Okay, and in a situation like this, what happens? You have a source that produces the wave, and you have a moving detector, okay? So the detector notices a different frequency, but then the sound wave reflects off the moving detector, okay? And at the source, you record a different frequency, yeah? So here you have moving f prime due to moving detector, but then when the wave reflects off the moving detector, you have a new frequency due to moving source, because the car acts like a source, yeah? Due to moving source. Okay, so yeah, the detector becomes a source. The detector of waves becomes a source of waves when the waves reflect on it. Okay, and because of this, the Doppler effect appears twice. And very strangely, this showed up in a problem given this year on the IB physics exam. The Doppler effect appears twice. Okay. And you can read more about this in the book. What is your homework for next week? Read section 9.5 and answer problems 11 and 12 on page 390. Okay. And I believe that this is all for today. Have a wonderful day.